This is Math 111, OLC Winter 2012, continuing on with Unit 4. Today we're going to talk about Section 5.1, entitled Exponents, and, entitled Exponents. Let's see, let me make this clear. We're going to start a new chapter today. Chapter 5 is entitled Exponents and Polynomials. Section 5.1, the first section in this chapter, is entitled Exponents. So we can't really talk about polynomials till we define what exponents are and learn the rules on how to handle them, or expressions concerning them. Alright, there are many rules, about 9 or so rules, regarding the handling of exponent expressions. I'm sure you're familiar with all of them. To what level you're familiar or unclear, we'll go over all of them here. Now I number these rules, the book does not, and there may be some wisdom to that, but I want to be sure, at least in my mind, to keep things organized. So I'm going to number these rules one by one and go through all 8 or 9 of them today. Rule 1. If I've got exponent expressions, namely I'm multiplying two exponent expressions that have the same base and perhaps different exponents, I keep the same base and add the exponents. So I'm going to call that Rule 1, and these are all listed in the book in a very nice 4-color graphic fashion. A simple example of this, well, say I've got x to the 11th power and I'm multiplying that by x to the 5th power. Well, of course, if you've got 11 factors of x multiplied by 5 factors of x, you'll have in total 16 factors of x. So very simply, I can apply Rule 1 and say it's x to the 11th plus 5th power, and that's x to the 16th power. Okay? Alright, some mild points of interest here. Let's say I've got y to the 4th power times y. Well, don't forget that y implies one factor of y. This exponent may seem redundant, and there's no exponent specified. Of course, we're assuming an exponent of 1, so y to the 4th times y, of course, reduces to y to the 5th power. Let's try 2 to the 3rd power times 2 to the 5th power. Well, if I've got 3 factors of 2 multiplied by 5 factors of 2, of course I'm going to end up with 8 factors of 2. And I know we don't have to always be so formal here, but at least the first time out I'm going to write this as 2 to the 3 plus 5th and claim that's 2 to the 8th power. Let's see, 8 factors of 2. Well, here I can actually evaluate this expression. Turns into a number of 256. Alright, Rule 2. Some books call this a power of a power. Well, what happens when you've got an exponent expression raised to another exponent? Well, of course, as you probably know, you can simplify that expression by multiplying the exponents. Simple example of that. Let me circle this. This is going to be Rule 2. If I've got x squared cubed, well, of course, again, I'm not going to always be so formal. That's x squared times x squared times x squared. And of course, if I multiply x squared times itself 3 times, I end up with x to the 2 plus 2 plus 2 is x to the 6th power. And of course, I could have taken the shortcut just by multiplying those exponents. That's what Rule 2 is all about. How about something like this? Another example. If I've got x cubed times x to the 4th, in turn raised to the 5th power. If I ask you to simplify this expression, well, I always like to try to simplify within inner parentheses first. X cubed times x to the 4th is x to the 7th. And of course then x to the 7th times x to the 5th power is x to the 35th power. So that would be my final return for that example. Okay. How about something like this? x squared to the fourth power excuse me, times x cubed squared. How would I simplify this? Well, x squared to the fourth power, of course, by our rule 2, that's x to the 8th, times x cubed to the second power is going to be x to the 6th. And now I can just add those exponents, keep that same base, and add the exponents, and I get a final return of x to the 14th power. Alright, so that's rule 2. Rule 3, sometimes called product of a power, or I should say product to a power. Again, the book doesn't number these. I'm numbering the rules. I am covering them in the same order that the book covers them, so be sure to notice that. I claim if I've got a product raised to an exponent, I can distribute that exponent over that product. This is what I'll call Rule 3, or product to a power rule. We can use this to good effect in something like this. If I ask you to simplify x squared y raised to the third power, of course, employing Rule 3, I could view that base as being a product of two elements, x squared and y, and I can then distribute that exponent over both of those factors in the base and multiply the result. Alright, so x squared cubed is x to the 6th power, and y cubed, y cubed is just y cubed, so I would call that return x to the 6th y cubed. Okay? Common mistake that might come up in something like this. Doesn't look too bad, but I think a lot of students might get this one wrong on test day, so please beware. If I've got 2y to the 4th to the 5th power, I think a lot of people would call this 2 times y to the 20th power, but that'd be wrong. Alright, let me show you why. This base is really built up of a product of two factors, namely the 2 and the y to the 4th. So if I distribute this exponent on both of those factors, I'll have to have 2 to the 5th times y to the 4th to the 5th. And formally, the 2 has to go for the ride also. 2 to the 5th power is 32. 2 times 2 times 2 times 2 times 2. And y to the 4th to the 5th power is, of course, y to the 20th by rule 2. So my final return there should be 32 y to the 20th. That's rule 3. Rule 4. Well, if you can play this game with a product, in other words, distribute an exponent over a product, you might think you can distribute an exponent over a quotient. The product really is a quotient in some ways. So if I've got a quotient raised to an exponent, yes, we're subject to restrictions. Y can't be 0, of course, etc. I can distribute an exponent over factors of a quotient as well. If I've got something that looks like this, let's say if I ask you to simplify x over y squared to the 4th power, well, all I really need to do is identify the different factors that make up that quotient and distribute them according to Rule 4. Right? X to the 4th power is x to the 4th power. Y squared to the 4th power, of course, the denominator is going to turn into y to the 8th power. So I'll write a final return of x to the 4th over y to the 8th. Would be my most simplified answer there. Another example of Rule 4. Let's see again. A problem like this on test day might lead to confusion. Let me write it down carefully here. Minus 6a to the 5th over b to the 7th. That expression, that quotient, in turn raised to the 3rd power. Alright, you can turn this into a lot of ink here. What I'm going to do is say this base is made up of 3 different quotients, or 3 different factors, in a product or quotient. There's a minus 6, there's an a to the 5th, and there's a b to the 7th. And what I can do is distribute according to rule 3 and rule 4, I can distribute that exponent over each factor of that product and quotient. Minus 6 to the 3rd power. Well, 6 times 6 times 6, that's 216, and negative 6 to the 3rd power is going to be minus 216. Don't forget, the minus 6 goes for the exponent ride also. A to the 5th cubed. Well, power of a power, you multiply the exponents, and 3 times 5 is 15 at the exponent level. Downstairs, b to the 7th to the 3rd power. Well, you multiply the exponents, 7 times 3 is 21, so it's b raised to the power of 21. So there would be my final return on that example, and I think the idea here is after you've done a few dozen of these, you start to spot the shortcuts and perhaps don't have to write down every single step. Alright, let's try another one. Let's see, this is still rule 4. 6x cubed over 5y to the 4th. I'm going to say raise that to the 2nd power. And again, you could spend a lot of effort and write a lot of ink for this problem, but I'm going to try to do it the easy way, the easiest way. I think the way with the least amount of ink. I've identified 4 factors in that product or quotient in the base expression. And I'm just going to raise each one to the 2nd power independently, and of course multiply or divide as needed. 6 squared is 36 in the numerator. X cubed squared is x to the 6th in the numerator. Downstairs, 5 squared is 25 in the denominator, and downstairs y to the 4th squared is y to the 8th power. Alright, so nice and easy. We get a final return there, and really by observation. Alright, let me talk about rule 5 now. Well, rule 5 is what they call the zero exponent rule. All this says is x to the 0 power equals 1. No matter how simple, no matter how complicated the expression, if you raise it to the 0 power, it's 1. Right? Well, that means 3 to the 0 power is 1. How about minus 7 raised to the 0 power? Guess what? It's 1. How about 3x squared y cubed z to the 5th power raised to the 0 power always equals 1. Anything to the 0 power equals 1. Right? That will come into play later on in the chapter. Alright, so let's go on to rule 6. Oh, let me get a new screen here. Alright, here we're going to start talking about negative exponents. So, rule 6 talks about negative exponents. How do we handle a negative exponent? That's an n there. Let me redo that. X to the minus nth power in fact, this is how we define raising something to a negative exponent. It's 1 over x to the nth. Notice the sign of the exponent doesn't have anything to do with the sign of the base. If we do a few brief examples of this, 3 to the minus 2 power, well, according to rule 6, it's going to be 1 over 3 squared. Basically, throw your expression down to a denominator level and change the exponent sign. So 3 to the minus 2 is 1 over 3 squared, and that, of course, reduces to 1 over 9. So remember, x to the minus n equals 1 over x to the nth. That is rule 6. That's one of 2 rules we're going to be using to deal with negative exponent expressions. Alright, next one we'll handle in a minute. Let's do another example. 7 times m to the minus 8th power. Let me rewrite this. There's an acronym I'm going to be calling up so often I'm going to list it for you here. Let's say I ask you to simplify an expression and express with positive exponents only. Alright, you'll see this a lot in this chapter, especially in this section. Our author has similar language. What I'm going to do is look at the first letters of all these words so I can simplify this instruction and use it a great many times with least ink possible. Simplify and express with positive exponents only. I'll say when I write the letters simplify and express with positive exponents only, this is the instruction to which I'm referring. Right? So in other words, we want all our answers simplified and we want all our answers to be equivalent with positive exponents only. Okay? Can't have negative exponents in your final answers. So if I want you to simplify and express with positive exponents only 7m to the minus 8th power, what will you return? Well, I think what the author is getting at with this problem is we have to perform the exponent operation first, then I'm going to worry about the multiplication. Well, the idea here is the 7 does not go for the ride here. M to the minus 8th is 1 over m to the 8th by definition, and then if I multiply these two expressions, I end up with 7 over m to the 8th power. Okay? Alright, so again, a common mistake is to put the 7 in the denominator also. Please note, the 7 stays in the numerator level. Okay? Alright, how about, well, let's try another one here. Simplify and express with positive exponents only minus c to the minus 1 power. Alright, I get all kinds of screwy answers for this one when I put it on test day, so beware. Maybe I can make things a little clearer. This negative sign happens outside of this exponentiation process. What I can do is say, well, if this makes it a little clearer, it's much like the example above. A negative sign in front is like having a multiplier of negative 1 times c to the minus first power. Of course, we'll perform exponents first, then multiplication. I'll get minus 1 times 1 over c to the 1, applying my negative exponent definition. All right, minus 1 times, well, c to the first power is just c. And if I multiply those two numerators, then I just get minus 1 over c. So in simplest possible form, minus, let me write that down again, minus c to the minus 1. If I ask you to simplify it and express it with positive exponents only, that's it. Minus 1 over c. Okay? Let's try something, another example of rule 6. Let's say I've got x to the minus 5th power times x cubed. Now there's a number of ways to handle this, and some ways take more ink than others. I suppose if we really wanted to be super formal, we would apply rule 1, where I'm multiplying the same bases. When I multiply the same bases, I keep the same base and add the exponents. Well, what if one of the exponents is negative? Well, guess what? You still add the exponents. Well, so I'll get x to the minus 5 plus 3 power. That's x to the minus 2 power. And if I want to simplify this, the final return would be 1 over x squared. So again, simplify and express with positive exponents only. SOPIO, I guess you might call that, okay? Alright, how about something like this? Let's say I've got a power of a power. Well, recall, what does rule 2 say about power of a power? Well, when you've got a power of a power, you multiply the exponents. Well, if you've got negative exponents involved, the rule is the same. You still multiply the exponents. Beware of the signs here. If I take x to the minus 3 times minus 2 power, that gives me a positive 6 at the exponent level. So that one's not as bad as one might think. Alright, let's talk about, I got another rule that's coming up here. Again, it's our second of two rules to deal with negative exponents. Well, we know from Rule 6, just to review, that x to the minus n equals 1 over x to the n. We just talked about that. Right? What about if you've got, let's say, a negative exponent in your denominator? How would you simplify something like this? Well, let me show you how. Well, x to the minus n power in the denominator, that's by definition 1 over x to the nth power, right? As you probably know, when we divide a numerator expression by a fraction, we invert and multiply. Some people say keep, change, flip. If we invert the divisor fraction and multiply by the numerator, well, guess what? Here it turns into 1 times x to the nth over 1, which of course simplifies to x to the nth power. So what I've done is really just proven Rule 7 for you. It claims that 1 over x to the minus n simplifies to x to the positive nth power. And that we will call Rule 7. Okay? Alright, so let me write those two rules next to each other. Rule 6, because they both deal with negative exponents. There's Rule 6, and here's Rule 7. Oops. And I suppose it's simpler to remember if you've got a negative exponent expression at the numerator level, you can just throw that expression down to the denominator level and change the exponent sign. And similarly, if you've got a negative exponent expression in a denominator, move it upstairs to the numerator level and change the exponent sign. Let me give you some examples of Rule 7. Suppose I ask you to simplify and express with positive exponents only, something like this. Alright, maybe I'm making this too simple. Well, Rule 7 says you just take this negative exponent expression in the denominator, move it up to the numerator. So it's going to be t to the 9th, t to the positive 9th power, and you're done. Right? How about something like this? Perhaps a little more interesting. Simplify and express with positive exponents only. If I've got 2 to the minus 3 power divided by 3 to the minus 4th power. What am I going to do? Well, very simply, I claim I can apply Rule 6 and move this downstairs to the denominator level as a factor and change the exponent sign, right? That's what Rule 6 says. And Rule 7 says I can take that negative exponent expression in the denominator, move it up to the numerator, and just change the sign. So a nice quick way to get things nice and neat and in recognizable fashion. So 3 to the positive 4th power is an 81, and 2 to the positive 3 power is 8. So this is an improper but reduced fraction, and I'll leave it just like that. Let's look at another one. And I want you to simplify and express with positive exponents only. Alright, so I see two different variables with two different negative exponents and two different parts of this fractional expression. The first thing I'm going to do, just to make things a little more clear, when I've got a negative sign sitting out front of a variable with a exponent on it, I can call that a coefficient of -1, could I not? Minus h to the minus 6 power is really equivalent to -1 times h to the minus 6, okay? All right, and similarly, downstairs, 8 times r to the minus 7th, that's like a factor of 8 in front of that variable with the exponent expression. All right, so of course I'm going to want to deal with these exponents first, then deal with the multiplication later. Well, the long and short of it is the minus 1 stays upstairs and the positive 8 stays downstairs, but these variable expressions will swap from numerator to denominator as indicated. All right, so r to the minus 7th comes upstairs as r to the positive 7th. H to the minus 6 comes downstairs as h to the positive 6. Oops. Please make this correction. I wrote 8. I meant 6. All right. So I suppose some might call this 1. Some might call this 1 as redundant. So your completely simplified answer would look like this. Minus r to the 7th over 8h to the 6th. Alright, let me get a fresh screen here. Let's talk about Rule 8 now. Rule 8 is really an extension of, let's see, what rule was it? Go back in my notes here. Really an extension of Rule 2. Alright, really Rule 1 and Rule 4. Kind of a combination of Rule 1 and Rule 4. Let me show you what I'm talking about here. Remember in Rule 1, when we multiply the same base expressions, we keep the same base and add the exponents. Well, as I'm sure most of you know, isn't this equivalent to when you're dividing the same bases? You subtract the exponents, you keep the same base, and subtract the exponents, namely the denominator exponent from the numerator exponent. Alright, so very simply, if I've got something that looks like this, b to the 7th over b to the 5th power. Now, there's more than one way to grind this out, but if you're looking to finish this with Rule 8, I just take my numerator exponent and subtract the denominator exponent, keep the same base, and subtract the exponents as indicated. Right? So b squared would be our final return there. Alright, of course, did I really need to be so formal here? Well, if you've got b to the 7th power, that means you've got 7 factors of b all being multiplied. That's what b to the 7th power means, right? If I've got 5 factors of b in the denominator, of course I can write that as b times b times b, etc., right? And when you've got common factors across a fraction bar, of course they cancel out. Well, that leaves me with 2 factors of b in the numerator and really a 1 in the denominator. So b squared over 1 equals b squared. So, do you want to do this by inspection informally, or do you want to grind this out with Rule 8 as I've indicated here? Either way is fine, I suppose. It depends which way you prefer. It depends on the problem situation. Let me give you another example here. Simplify and express with positive exponents only. 2x to the minus 5th power over x to the 11th power. Well, again, the factor of 2 I'll deal with in a minute. I'm going to deal with these exponents first. I claim that x to the minus 5th over x to the 11th is really 2 to the x minus 5 minus 11 according to Rule 8. And if I subtract those exponents as indicated, I'll get 2x to the minus 16th. But of course, if I want to simplify and express with positive exponents only, x to the minus 16th is 1 over x to the positive 16th by rule 6. And I suppose in simplest possible fashion, in simplest possible form, I would write my answer as 2 over x to the 16th power. Okay? Here's another one. Simplify and express with positive exponents only. Alright, a lot going on here. Here you got in the numerator, you got a negative exponent base raised to another power. And similarly in the denominator expression. Alright, what I'm going to do is independently work these outer exponents on both the numerator and denominator. Well, if I look at the numerator, a to the minus 2 cubed, by definition, that's a to the minus 6th power. I multiply the exponents. Be careful of the sign. If one of them is negative, that's fine. You multiply 3 times minus 2, okay? How about downstairs? A squared to the minus 4th power. Of course, that turns into a to the minus 8th power. Now, there's a number of ways you could go here. I suppose I could say, well, if you want to formally use Rule 8, when you're dividing the same base expressions, you keep that same base and subtract the exponents, namely subtracting the denominator exponent from the numerator. But be careful, both these exponents are negative, so you got to keep your signs straight. Alright, so minus 6 minus minus 8. This new exponent turns into a positive 2, does it not? Minus 6 minus minus 8 is a squared, and you're done because you've expressed it as simply as you can with positive exponents. I suppose I could have said also this if we take it from this point. Same example. Could I not say this comes upstairs as a to the 8th power, and then this comes downstairs as a to the 6th power? So I can informally say that 6 factors of 8 in the denominator cancels out all but 2 factors of 8 in the denominator, and I get the same answer a little more informally. Okay? Let's try another one. Simplify and express with positive exponents only. A little nastier. Alright, what I'm going to do here, now let's see, I've got a quotient and product expression mixed, raised to the minus 3 power on the outside. What I'm going to do is, before I apply that outer exponent, I see I've got powers of b that I can combine into 1 power of b. So I'm going to simplify that base expression first. I'll do that right here. Well, I claim that b to the 5th power over b to the 8th power, that's equivalent to 3 factors of b in the denominator. Please convince yourself of that. If you've got 5 factors of b in the numerator and 8 factors of b in the denominator, 5 will cancel out and I'll have 3 factors of b left as a residue in the denominator. Alright? So I've simplified as far as I can within those base parentheses. Now I'm going to apply rule, really, what's it, rule, I'm going to cite the rules, you should do it right, hang on a minute. And it really rules 3 and 4, claiming I can distribute an exponent over factors of a product or quotient. A squared to the minus 3 power is a to the positive 6 power, right? 5 raised to the minus 3 power, that's going to be 5 to the minus 3 in the denominator, right? B cubed to the minus 3 power, that's going to give me a b to the minus 9th power in the denominator. Okay? Alright, so if I grind this out, well, there's some room here. 5 to the minus 3 power can come upstairs as 5 cubed. A to the 6th power is already upstairs. B to the minus 9th power comes upstairs as b to the 9th power. And if I take everything out, if everything gets transferred upstairs, that leaves an invisible 1 as a factor in the denominator, which of course is a redundant denominator. So I know that 5 cubed is 125, a to the 6th is a to the 6th, and b to the 9th is b to the 9th. This would be my final return, most simplified return for the above problem, simplified with positive exponents only. Okay. The book talks about one more rule, Rule 9, and it's a nice little shortcut. Actually, I could have used this shortcut in the previous problem. Let me show you what I'm talking about. It says if I've got a fractional base raised to a negative exponent, I can equivalently invert that fractional base, should be an x there, and raise it to the positive nth power. For example, let's say I ask you to evaluate 2/3 to the minus 4th power. Again, simplify and express with positive exponents only. That is our task for this problem. Well, according to Rule 9, all you got to do is invert that fraction, that fractional base, and change the sign of the outer exponent. Then it's a breeze. 3 to the 4th is 81, and 2 to the 4th is 16. 81 over 16, right? Let's try another one. How about y squared over x cubed raised to the minus 3 power? Alright, anytime I see an outer exponent that's negative working on a fraction, I can invoke this Rule 9. And it may make my life a little easier here. So invert that denominator, that base fraction expression. Let me make sure I did it right. X cubed over y squared to the 3rd power, changing the outer exponent sign. Hence I get x to the 9th over y to the 6th. Completely simplified with positive exponents only. Alright, let me get a fresh screen here. We'll do 2 more examples today. Alright. Simplify and express with positive exponents only. Now don't run away. 8 to the minus 2 power times b cubed over a squared b cubed b to the 4th power. All this raised to the minus 3 power. Alright, now again, I think if you're like me, you like to do these problems with as much finesse and the least amount of ink possible. what I'll notice here, before I work on this outer exponent, I'm going to notice all these factors inside this product and quotient have similar bases, right? There's powers of A and powers of B. I can claim I can simplify this base expression before I work this outer exponent on the expression. Powers of A, I claim a to the minus 2 power over a squared. I can combine that into 1 power of a. Well, a to the minus 2 power comes downstairs as a squared, so I'll have 4 factors of a in the denominator. Similarly, b cubed over b cubed times b to the 4th, the b cubes cancel out, and I'm left with b to the 4th in the denominator. And if I cancel everything out in the numerator, that leaves an factor of an invisible 1 upstairs. Okay? Alright, this looks a little messy, more than a little messy. Let me try this again. Let's say a to the minus 2 power times b cubed in the numerator over a squared, b cubed, b to the 4th power. Okay, bear with me here. I know it's a little nasty. That entire expression raised to the minus 3 power. Let me take it a step at a time. Maybe a different color would help. I claim these 2 powers of a can be combined into 1 power of a. A to the minus 2 over a squared indeed reduces to a to the 4th in the denominator. Please convince yourselves of that fact. The b cubes are common factors over a fraction bar, so they'll cancel out. And then the b to the 4th power will just be carried over into our fractional expression in the base. Okay? Alright, so simplifying that base expression, I get a much more pleasant thing to handle now. Maybe that color coding will help. Now I notice I've got a fractional base raised to a negative exponent. I can invert that fractional base and change my exponent sign according to Rule 9. Well, of course, a divisor of 1 is redundant. So this is equivalent to a to the 4th times b to the 4th cubed, which of course reduces to a to the 12th times b to the 12th. And that is my final, completely, most simplified answer with positive exponents only. Alright, I'm going to do one more. I think it's one of the last ones in your homework list. Let's see, it's going to do, this is number 105. Exercise number 105 on page, what page is it on? 404. Let me check it. You want to turn there yourself. No, not 404. Hang on a minute. It's number 105 on page 407. I think I checked. Alright. Now, don't run away. This one looks a little nasty, just like the last one did. We've got kind of a complicated expression. 4a squared b cubed z to the minus 4th power in the numerator divided by 3a to the minus 2 b to the minus 1 z cubed in the denominator, and the whole mess raised to the minus 3 power. Alright, I'll ask you to notice like we noticed in the last one. These expressions invoking powers of a can be combined into 1 power of a. Similarly, these powers of b can be combined into one expression in b. And these powers of z can be simplified into one power of z, thus greatly simplifying our work for the rest of the problem. And let me see if I can do this. We can do this in our head, or at least a little bit. Alright, 4 over 3 is already reduced. That's not going to simplify. A squared over a to the minus 2 power. If the a squared comes up, if the a to the minus 2 comes upstairs as a squared, I'm going to have 4 factors of a in the numerator. Similarly, if the b to the minus 1 power comes upstairs as b to the first power, I'm going to have b to the fourth power in the numerator. And if z to the minus 4th power comes downstairs as z to the 4th power, I'm going to have 7 factors of z in the denominator. Looks a lot better. Don't even need it such a big fraction bar. Alright, so notice I have not applied that outer exponent yet. All I've done is simplify the fractional base expression. Of course, I'll notice now I've got a fractional base raised to a negative exponent. I can invert that fractional base and change the exponent sign to make quick work out of this problem. Alright, I can't simplify anymore within that base expression, so I'm going to claim I have 5 factors that I have to apply that positive 3 exponent to. Alright, so 3 cubed is going to be 27 in the numerator. Z to the 7th cubed is going to be z to the 21st power in the numerator. 4 cubed, 4 times 4 times 4, that's 64 in the denominator. A to the 4th cubed is a to the 12th power, and b to the 4th cubed is b to the 12th power. I'm done. I have simplified and expressed that rather nasty looking expression with positive exponents only. Alright, problems like this represent the upper limit of difficulty in this section 5.1. These are the building blocks for chapter 5, so be sure to spend quality time in this 5.1 section. And this concludes the video for section 5.1. That is all.